Everyone. First of all, I would like to thank the organizer for putting together this very interesting workshop, and this concludes by this conference and allowing to bring many communities together to talk about problems or interesting problems about neutrino physics. So this morning I will talk about how to relate the axial form factor data from lattice QCD. We already had 3 talks on it to Neutrino-Nucleon data. And this afternoon you will see the experimental part of this. This is a work in collaboration with Alex Friedland, that everybody knows here, Sergi Gonzalez Solis, that was postdoc in my group and now moved to Los Alamos, Kevin Kirian, that is his main, the main part of his thesis at Indiana University, and RAU student that is now in Maryland, Clayton Risto. So this is the outline of my talks. First, I will start with a brief introduction and motivation. Why it's interesting to link or to bridge lattice QCD with neutrino measurement. Then I will show you our exploratory studies, and then I will also show you some work that are also in progress about prospects for improving the axial form factor parametrization before concluding. Okay, so accurate neutrino measurement requires the knowledge of the cross-section. So you can write like the measurement as a function of the incoming flux times some modeling inputs that rely on the cross-section times some detector parameters. So we need really to have a absolute cross-section to relate observed rate to oscillation probability. And so an accurate physical model of neutrino-nucleus interaction is also needed for a precise neutrino energy reconstruction. To reconstruct the energy, you are thinking of measuring the energy of all final state particles and add them up using the calorimetric method. In a realistic experiment, not all energy can be accurately measured. Yes. So then we need a cross-section model to improve the energy measurement by filling out the missing information. So we require the most accurate physical model of interaction. As you can see on this famous plot, you have different processes involved depending the energy of the neutrino, right? For the cross-section. So at low energy, the cross-section is basically dominated by what we call quasi-elastic processes. So a neutrino interacting with one nucleon and giving you a charged lepton plus nucleus, I mean proton and neutron. And then when you increase energy, you start to maybe increasing the difficulty of the problem, right? Because you start to produce more particles and especially pion production. And then you have this intermediate energy region, which is called the resonance region, where you create many particles and resonance. And then you, at higher energy, then the deep inelastic scattering is dominating. Yes. So then this, as you can see, your problem is much more involved. It's much involved. Is quite complicated because you need to have nuclear uncertainty or hadronic uncertainty for every under control for every energy scale. Yes, and you are like going over all this energy in one measurement, which is quite remarkable and difficult. Okay, so in this talk we will focus on the quasi-elastic scattering process that happen at lower which is dominant at low energy. And so it's basically, it can be naively represented by this picture where a neutrino interacts with one neutron inside the nucleus, and then one proton is ejected plus a muon. Okay, so my hadronic matrix element transform a neutron into a proton, and it goes through this current, and then I can write it in full generality in terms of the so-called form factor, yes, that describe how the quark hadronize into my nucleons. So there, here I wrote it in terms of 4 form factor because I assume isospin limit, and then I have 2 form factor F1 and F2 that are linked or related to the vector current of my process, okay? And this can be extracted from precision electron data. Yes, for instance, at Mainz and JLabs, there have been a lot of experimental experiments really scattering electron on neutron and proton, and they have determined this form factor with a very good accuracy. And then I have the axial part of my matrix element can be written in terms of the axial form factor and the induced pseudoscalar form factor. Yes, we saw this just in the talks before. And so if I look at this induced pseudoscalar form factor, I can relate it using this partial conservation of axial current to the axial form factor and the pseudoscalar form factor. This is the so-called generalized Goldberg-Treiman relation. And Sarah Collins told us a lot about this relation and how is it computed on the lattice. Now, if you assume pion pole dominance, you can relate this induced pseudoscalar to the axial form factor, okay? And so, as you can see from these formulas, then your main unknown is this axial form factor, yes? Okay. And this axial form factor also, if you make the calculation, you see that it provides us the largest contribution to the quasi-elastic cross-section at 1 GeV. And we cannot determine it experimentally using electron data, because electron data goes through the vector current through a photon, yes? So I don't have axial information there. So in the following, we focus on this axial form factor. We already heard about its determination on the lattice, and we will see what are the implications. So what is known on the axial form factor? Well, it's an old problem, okay? Traditionally, it was assumed to follow this simplistic parametrization called the dipole parametrization. We assume that the axial form factor is dominated by a double pole, okay? And this is mainly driven by the high energy behavior of the form factors that has to go like 1/q to the 4th, okay? And so we have the 2 parameters to determine in this parametrization, which is the axial form factor at 0 momentum transfer, this GA, that we have seen is extremely accurately calculated on the lattice, and also it's well measured from neutron decay, and the axial mass, MA, okay? So this the axial form factor used to be determined using a combination of processes, of experimental processes, neutrino-nucleon cross-section, okay, neutrino on hydrogen or deuterium, and pion electroproduction, because using some chiral perturbation theory at low energy or low energy theorem, you can relate the slope of this form factor to the measurement of a pion electroproduction. So a gamma star to a nucleon giving me a pion and a nucleon. These are the compilation of results presented in this paper in 1999, where you see on the left the axial mass average extracted from this old deuterium and hydrogen data, and on the right, the axial mass extracted from this pion electroproduction. And what you can see immediately is that these 2 results agree well together, okay? So if if you will take them like this, you say, okay, there is no problem. I have an extremely precise axial mass that has been determined in two different ways, okay? But if you look closer, okay, to this experiment, these are bubble chamber experiments that are quite old, and they were very challenging at the time, yes? You needed to know the flux, and you needed, so there were people counting the number of events, okay? So this is not a very precise measurement. And for the pion electroproduction, you have also challenges, because in principle, you can extract this axial mass or this radius only at very low energy where the low energy theorem works. Otherwise, you have corrections that you have to compute and that nobody knows how to compute. And then recently, there has been two significant progress on this axial form factor determination from two fronts. The one front is a new measurement of cross-section coming from recent experiments, Mini-Boon, K2K, Minerva, and Nomad. And here they have been measuring the differential cross-section, yes? So here you have a measurement from Mini-Boon, which is a cross-section as a function of the kinetic energy of the outgoing muons and the cosine of these muons, okay? And then you have this measurement from Minerva, which have measured the cross-section also in terms of the perpendicular direction of the muons and parallel with respect to the incident neutrino. And here you see that what they have fitted the axial mass for some measurement, and for Minerva they have assumed the genim axial mass by default is assumed to be 0.99. When they have leaving the axial mass free, you see that this axial mass, the result is around 1.2, 1.3, except for Nomad, which is in agreement with the older determination. But the others, they really have enhanced axial mass. Okay, and this was actually known as the Mini-Boon puzzle for a long time. But actually, it was confirmed by K2K and by Minos. And then we have another significant progress that has happened in lattice QCD, as you heard in the talk before mine. Here I have maybe a older picture compared to what was presented coming from a paper in 2018, where you see the determination on the lattice of this axial form factor at zero momentum transfer, this so-called GA. And you see that the lattice have made impressive progress, that they match the experimental precisions. You have all the experimental measurements here with the PDG average here that you can find also in this band here. And you see that they are almost at the same precision, which is rather impressive. And they agree with the experimental measurement, which is also impressive. And then on the right plot, you see the radius, axial radius, which is the derivative of the form factor at zero momentum transfer. And here you have the neutrino deuterium data and the extraction using dipole from electroproduction that I showed before. And this is a reanalysis of the same work and of muon capture using the zip expansion. And this is a comparison with the lattice in 2018, the value of the lattice group, okay? So this was the situation basically for the axial form factor before 2018. What I plot here is the axial form factor as a function of Q squared, okay? So the momentum transfer squared exchange between the two nucleons. And what do you see? You see that I have plot the dipole parametrization using this axial mass of 1.05 that was found in 99, for instance, and I have the dipole mass of 135 that was a mass found by Mini-Boon, for instance. And then I have the ETMC work and PNDME in 2017. And since after 2018, it was found that there was a problem with the PCAC, as you heard this morning, and PCAC was, or generalized Goldberg-Riemann relation, was not satisfied, and they found that it was mainly due to excited state contamination. And what happened for instance, PNDME results and so forth, they result now doesn't follow this red curve, but is follow first the green curve at the low, very low energy, and then it's converged towards the red curve. And what you can see is all the recent lattice determination all agree with this behavior. So what we would like to bridge this new lattice result with a neutrino measurement. That means we would like to connect the predicted axial form factor to the measured total and differential cross-section. And then at the moment, we have just interpolate between the lattice point in this dashed black line. And then we would like to create in the future a physical motivated analytical parametrization, which can be used to assist and complement the lattice simulation going beyond the dipole. Because here you see that with the new lattice simulation, they cannot be fit with the dipole. Yes. Okay, so how do I connect this lattice calculation to the experimental measurement? Well, at the very minimum, we tried the very simplest model, which is just using a relativistic Fermi gas model to explore this, how the change in the axial form factor change the prediction in the cross section. Okay, so the idea is the question we want to address is which Q-square range is important for neutrino cross-section data? If one changes the functional form of the axial form factor, how does it impact my cross-section prediction? And then using this prediction, we can see what should be the size of the two nucleon currents and other nuclear effects that we need also to understand this problem. Okay, so do lattice agree with the recent experimental data? Well, here I plot the integrating cross-section, okay? That is in green here for the axial mass of 1.05, so the old one, and the axial mass, the red one of 1.35 GeV. And then I will show you my prediction for the empirical parametrization. And here we have put the mini-boon experimental data point, and then we have also tells you which Q-squared are dominating, okay? So the blue is the Q-square between 0.0 and 0.2. The orange is 0.2 and 0.4 to see which Q-square are contributing. And we see that at an energy, for instance, of 0.5 GeV, the cross-section comes mainly from Q-square below 0.6 GeV square. That means lattice QCD has to focus on very low energy, yes, to be the most precise, to make an impact on, for instance, to predict mini-boon cross-section. At 1 GeV, we have seen that 40% of the contribution comes from Q-square between 0.6 and 2 GeV squared, okay? And this is the actual prediction for this empirical nucleon axial form factor. You see that it's basically in good agreement with the data, leaving some room for nuclear effects. And now I not only have the integrated cross-section, but I have actually the full differential distribution that I can use, yes, for different kinetic energy of the muons as a function of cosine of theta, yes. And I can make the same exercise with this empirical parametrization to predict my cross-section and see which Q-square are entering the game. And you see that the agreement is quite good. So these are for different value of energy of the muons. This is for mini-boon. What about Minerva? I can play the same game for Minerva using then the integrated cross-section for low mass of the axial mass, low value of axial mass high value of axial mass. And then for the empirical parametrization. And what I see here, the situation is similar, but for the neutrino is energy for Minerva is higher. So the relevant value to compute for the axial form factor are q squared smaller than 2GeV. Okay. And then I can play the same game with the differential cross-section. In this case, their kinematic variable are this transverse and longitudinal momentum of the muons. And I see that again, that my empirical parametrization reproduce quite well the data. Yes. So from this study, I conclude that the empirical parametrization is in relatively good agreement with Mini-Boon and Minerva data, while still leaving some room for nuclear effects. So this allows us to quantify nuclear effects present in this neutrino-nucleus scattering. They appear to be of the same order than for electron-nucleus scattering. They were quantified to be like a few percent by Arthur and Koski talks in week 2 of this program. So this seems much more reasonable than the 30% that was postulated when the Mini-Boon analysis came out to explain this discrepancy with the old dipole assumption of an axial mass of 1GeV. Okay, now the second question I would like to address in my talk is, can I improve the axial form factor parametrization? So you remember that we say that we had the recent lattice results have shown that this dipole parametrization that was just allowing to vary two parameters, the form factor at zero momentum transfer and the mass of the axial mass, is not accurate enough to fit the lattice results. We need more parameters. This parametrization is over-constrained. Can we improve this parametrization? Well, in principle, yes, because we can use complex analysis and analysis property of my form factor to try to improve. How can I do that? Well, I know the form factor is analytic everywhere in the complex plane, except that it has a right-hand cut where you can produce hadronic states here between n and n bar. Okay, and remember that the processes happen in the unphysical region of T smaller than 4 mass of the nucleon squared. Yes, in the T channel. So there have been some work that have used the so-called Z parametrization to offer a better parametrization of this axial form factor. These are the work in these two papers, for instance, where what do? They map the analytical, they map the cut into a circle, okay? And then they expand around the so-called Z parameter, where they expect the convergence to be much better. Okay, so this allows you to have many more parameters you can fit. These are the so-called AK. Okay, and then you have to study still the convergence of U fit, and then but you have much more freedom to fit your lattice data. And the question we wanted to make is, can we include also physical inputs? How? Well, I can use Cauchy's theorem and relate the form factor that is analytic everywhere except on this right-handed cut. And I can close my circle like this and use Cauchy's theorem and relate the form factor to his discontinuity below and above the cut. So related to his imaginary part. From knowing his imaginary part, you can determine it on the anti-complex plane. But you need to know his imaginary part from the threshold to infinity. So here we consider this axial current coupling to two nucleons. So the first intermediate state that has the right quantum number is dominated by 3 pions. Okay. So what we can do is we can use unitarity and put all the states that are allowed by the having the right quantum number, and write that the imaginary part of my form factor is the axial current going to 3 pion, and then time 3 pion going to n bar. Okay. So now if I know this amplitude, then I can reconstruct my imaginary part, and then I can close the circle here, provided that the form factor converge. I can write, I can have a parametrization for the form factor, or I have a description of the form factor. So how can I find this the so-called spectral function or imaginary part of the form factor? Well, one side, axial form factor coupling to 3 pi, I can get it from my measurement of tau decays to 3 pion, because it goes through the axial current. And I can use some measurement by Aleph and more recently by Babar and Bell. Okay. And the other part, well, other part is a bit more complicated. So 3 pion coupling to n bar. And there have been some model proposed in the 80s using vector meson dominance and using this exchange of delta pion and rho. And so you can build a model to determine this part. And then using analyticity, you can reconstruct this axial form factor. This is still a work in progress, but we are hoping to get physical parametrization soon. So let me conclude. With neutrino physics entering precision era, we have new demands for better understanding neutrino-nucleon interaction. Lattice QCD predicts that the dipole ansatz is insufficient to describe the axial form factor in the range relevant for neutrino scattering. Precise lattice data is needed across the anti-range from Q squared between 0 and 1 GV squared in order to effectively parameterize the axial form factor. The Q square dependence of the axial form factor predicted by recent lattice calculation are in relatively good agreement across the anti-range of energy and scattering angle measured by Miniboon and Minerva. And then the precise knowledge of the axial form factor gives us a way to directly determine the size of this nuclear effect that we have to hunt in neutrino-nucleus scattering that needs to be determined and understood. Thank you very much.
Thank you so much, Emilie.
Thanks. Before I ask my question, I noticed there's a pair of keys here.
Yeah, it's mine.
Oh, okay, sorry. Okay. So thank you. One question I have is the comparisons you show with the Miniboon or Minerva. So
yes.
My understanding is that there's kind of two unknowns. One is the impact of the axial form factor, and the other one is the other nuclear effects that are missing in the prediction. So I'm just not quite sure how do you draw the conclusions on whether there's agreement or not based on the fact that you're testing the axial form factor, but also missing this component?
Yes, so basically, if I trust my result on the axial form factors that are extremely precisely measured from lattice QCD, I can say then, okay, the disagreement between my data, like the small disagreement, give me a size for my nuclear effects. And in principle, if I improve my nuclear model now, I should, I hope, get an agreement. Yes.
Okay.
But it's one step in the direction of getting a precise cross-section by including one nucleon effect, if you want. Yes.
Okay. Thanks. Okay. Another question. So I see you're including the Minerva and Miniboon double differential measurements. Yes. Are you thinking, or have you thought of using a microboon double differential cross-section also in lepton?
Yeah, we would be really happy if it's available. This was only for quasi-elastic, right?
Oh, you want
whereas
specific...
microboon is for
inclusive.
Ah,
so
this we didn't do because it's much more involved. Yes.
Okay, so you would need a quasi-elastic slide. Yeah, of course.
Yeah,
okay,
yeah.
Thank you.
This is just a, yeah.
Yeah, so when you say nuclear effects, does this refer to 2P2H processes? Since my understanding was that a large part of the discrepancy between the original parametrization and mini-boon is due to 2P2H, right?
I mean, it could be explained by this, yes? This was
Yeah.
something that was explored by nuclear physicists when mini-boon went out with this discrepancy. They say, okay, let's imagine that the axial form factor is well known to be axial mass 1.0, and then let's see what will be the 2P2H effect to reproduce this differential cross section, yes, or this cross section, yes, and then they found a 2P2H of order 30%, but the problem is like in electron data, you don't see this enhancement, yes. 2P2H, you don't see this huge enhancement, and you will think naively maybe that you should have the same order of magnitude, right? Because these nuclear effects are independent if you shoot your nuclear target with an electron or a neutrino, no?
So what you're saying is that when people explained this via 2P2H, they basically left the normalization of the 2P2H as a free fit parameter.
Yes,
and then of course you
have
can do
many
it.
parameters in their model. Yes.
Yeah. And may I ask another question? Can you go back to either slide 19 or slide 35, where you show this plot that illustrates this one. So there are a few data points that lie on the red curve, and then the bulk of the points lies on the black dashed curve.
Correct. So sorry, I didn't maybe explain myself well enough. These data points that lie on the red curve come from the same lattice collaboration, but before 2018, yes? So you see ETMC and Gupta et al. 2017.
Okay.
And after making more simulation and including this excited state, trying to remove the excited state contamination, they arrived to the result in ETMC 2020, which are these purple you see here, and Gupta 2019 or 2021, and they have basically the result have shifted.
Okay, got it. Thanks for the clarification.
Thank you.
Thank you for the nice talk. So maybe you said it and I missed it, but some people discuss GA and whether we understand that value.
Yeah.
And there's some disagreement on neutron lifetime, and some people also speculate on the unitarity of CKM.
Okay.
Is this a level of precision that impacts neutrino experiments or no?
Good point. Yeah, so you have this neutron decay measured differently, right? Like by this bottle experiment and by this beam experiment, yes? And what you are saying is that, can I see this in the neutrino? I haven't thought about it. I would expect that the level of precision is not, in the neutrino physics community yet, is not at this level to see the difference, but it's a very good question and I have to investigate it. Yeah. Thank you.
So I think some of the discussion about the experimental results, I would add a note of caution. Like
yes.
Both you and David said CCQE measurements. There are no CCQE measurements. That's not a thing we measure.
Yes.
In the experiments.
Yes.
So
CCQE like, yes.
Sure. Yes. Yeah. Although, like for the mini boon measurement, there are two, right? I wasn't clear whether you use the corrected or the uncorrected version, which obviously has problems.
Yes. So we could trust more maybe Minerva, or it's more recent, and maybe they do this CCQE like.
Yeah. So the uncorrected mini boon measurement, I think it has its problems, but the central values at least are fairly trustworthy. The corrected version has effects like 2P2H already subtracted. It's not the full 2P2H model, but they do have like planarness delta decay subtracted, which is a large chunk of what we now call 2P2H. And so I think you have to be very cautious. So I would definitely favor.
But this is a big problem for us. So this would be great if the experimentalists could give us really what they measure and without correction, you know. because the problem of the correction, if we will trust, like if everybody will believe in this model, right, in the nuclear physics, and if it will come from first principle, I would maybe agree that you make the subtraction. The problem is that if you make the subtraction, then we cannot, if we have new ideas, right, and we have new models, new idea to explore, we cannot go back, yes?
No,
This
that's
is a big
exactly my
problem.
point. Yeah, no, I 100% agree with
And
that.
for instance, here, Minerva, they assume this MA of 99, yes? And then they make the huge correction with Jenny, yes? On their model, for instance, to reproduce the data. But what would be good, but you see that Miniboon, they had 1.35, but K2K and Minos are not very far, yes?
Well,
They agree for this.
yeah,
axial
sure.
mark.
I mean, I think there's a lot of issues now kind of being conflated. I mean, I 100% agree that experiments should not correct their data.
This
And
would be the best for us. I mean, for us, for the communities, yes?
Sure.
Otherwise, the data are lost.
Yeah, no, I absolutely agree. And that is why modern measurement should be preferred, I think. The fit values in the model dependent fits is kind of a separate issue, I would say.
And I agree with you that, I mean, every experiment should also, fit and propose to extract quantities. This I agree. But we should have an access to the data as extracted, yes? Thank you. Yeah.
To comment on the comment, there are several moving parts in all of these things. There are nuclear effects, which are a collective term that actually describes several things, right? So there, you know, two nucleon currents, but also final state absorbed pions. So to make it, and when you see this difference, it's supposed to encapsulate both of them. Or when Minerva do their things, they simulate with Gini what happened to the pions and how many of them were supposed to be. So like there are some things where data is above the quasi-elastic prediction as it should be. If it was below, we'll be worried. But there is an interesting statement here. So you decide which ingredients you're going to trust more today. And I think there is at least value in taking these lattice predictions that have made tremendous progress seriously and say, well, what if we take them seriously? And then two things turn out. It turned out that you are much closer to the overall data than if you were with the old dipole. And second, the double differential cross-section, not just the overall rate, but the double differential cross-section is followed pretty well. And so the assumption where you were insisting on the old dipole, like in a rigid dipole with this 1.05 thing, it requires you to invoke two nucleon currents, which are 10 times bigger than the corresponding measured in electron scattering. I mean, Arthur may talk about this today, I don't know. But he talked about this on week 2. So first of all, these two nucleon currents are very difficult to observe in electron scattering. People had to work very hard to identify them. And in neutrinos, we have to assume they are 10 times larger. And second, that their double differential distribution is such that they are able to fake what you would get with one nucleon current bin by bin. So they're very clever, these things. They are there just to, you know, match in the double differential cross-section this detailed information that you could get by using what lattice computes now for a single nucleon. So it's not, you know, it's not crazy to revisit this point to say what if lattice is correct.
I absolutely was not saying that it's not. I was just saying we need to be careful in the data we compare to.
Yeah.
But I don't agree with that.
Yeah, we just have to make sure that when we use something which is corrected, or where the analysis postulated to have 0.99 for MA at all like Minerva, and in this table, different countries don't mean the same thing.
Yeah, but I mean, okay, I'm a bit confused about what you just saying. But if Minerva have an MA of 0.99 in their model dependent fit and also in their Monte Carlo, when they extract the result, as long as they do the analysis correctly, that shouldn't bias the result in any way.
Well, if you insist that your one nucleon path is determined by the dipole with MA 0.99, then you're going to get this tremendous thing that you will ascribe to the two nucleon path. We're going to ascribe 35 or so percentage of refraction. And so then this is what we're saying. There are several ingredients here, but some could be trusted more than others. Some could be taken and the others inferred. And I guess the main argument is that right now, it's the two nucleon things that have to be inferred. The one nucleon things that seem to be in much better shape in terms of prediction.
But
again, I don't agree with what you're saying, Paul. I'm just saying that some of the data is better to compare to than others.
yeah.
But I agree with everything else you said.
No, but what you say is that in principle you take some input maybe to do you Monte Carlo or something like to analyze your data, but at the end like your result should be independent of the input you put in the beginning, right?
Yeah, and modern measurements are very careful to check that they are as robust as they can be to the input source.
Mm-hmm.
It's not always perfect, and all the measurements, particularly the corrected is very flawed because of that.
Yeah.
So, you mentioned 325
So are there any other questions? If not, then I will take over and I will ask a few questions. So first let me start with a comment which may be useful to your analysis. I think page 19, but it's a wild guess. No. Okay, so somewhere you have data from Minerva,
Yes.
and you need to be very careful. From what I remember, total, there's a general
Total
reflection.
or
Yes.
yeah.
So it's a general reflection. In neutrino physics, every set of data comes with a huge caveat. I would say pages of caveat.
Mm-hmm.
In the case of Minerva, from what I remember, total means not really total, but total which is measured by Minerva, so only angles below 20 degrees.
Yes, we put this in.
Okay, so then you did it well.
Yeah, we had the problem at the beginning because we didn't look at this, and then we were very far away.
That's perfect.
Yeah.
So on page 15, I think, or 16. Yes, here. So you need to be very careful looking at this because it's extremely poorly discussed. Sorry, in the original paper, or it's extremely poorly remembered. I would say that's more accurate. So typically, when we look at this table, we recall, these are Deuteron data, which is, I would say, completely wrong. There are probably 3 experiments which are actually based on Deuteron. Many of them come from neutral currents on nuclear targets. So this is a mixture that we wouldn't do today, because today we are much more careful. So it's a mixture of mostly something heavily corrected for nuclear effects, like freons, what's not, some really strange nuclei for us. Mixture of deuteron, antineutrinos, neutrinos. It's a complete mess if you look at it very carefully. And the highest statistics is, I think, 2,000 events. So if we want to decide on what should be used by Dion with millions of events based on that's not really appropriate. I had some more comments, but right now I think I forgot. We can discuss it. Oh yes, Nomad. So Nomad, if you could go back to Nomad. Nomad, yes, this one. Yes. Nomad requires So Nomad requires lots of caution because that measurement of the axial mass is largely based on the total cross section, not completely, but largely based on the total cross section.
And their agreement, right?
Their nuclear model actually provides free energy. So
here I put Nomad.
Yes. So if they used, because so that cross section is extracted with some extra assumptions which are hardly non-trivial. And the value of the axial mass relies in fundamental way on those assumptions.
Yeah. This is for sure, yes. So this was also mentioned that depending on the assumption you make, you extract a mass.
So if you look in their table, that value in principle could be around 1.2 without any issues. Just depending on the choices, this is what they selected. But there's very little change in chi-squared when you go to something around 1.2.
Reading this whole bubble chamber literature was very interesting because when we look at this, it looked like these were the groups, the BNL and the argon groups were in competition to get a smaller error bar. When you look at their data and you look at the different fits, it's not obvious that, how one is better than the other, or you have to rely on them being able to count things very well at low Q squared and stuff like that. But then it looked like it's just a race, and the figure of merit was to get a smaller error bar. Well, that was then. And now 40 years ago, we're somehow stuck with these results, and we are deciding how much to P2H we have to add in the NOVA or Dune simulations in order to explain a very relevant energy range based on, something that looks very, very dubious in retrospect. It would be great to redo this in some form. So we heard from Daniel Rutherboris that they're trying to isolate proton contributions to scattering in Minerva. That's a tough job, but I guess that's the best we can do these days, because otherwise you cannot build a bubble chamber. It will not pass fire safety inspections or something like that.
For example, BNL experiments were done where these are, I would say, roughly carbon data, neutral currents, which determine flux, assuming that we know CCQE perfectly. So it's not really an independent measurement, and that brings me to the issue of the flux. Recently, there was a paper which questions the determination of fluxes based on the extrapolation to zero energy transfer, which I think is very important. If we get our fluxes wrong as a general statement, not addressing any particular experiment, if we get our fluxes wrong, then our extractions of the cross sections are extremely surprising, and it's very hard to make any sense of them, because by the time that we get to this step of the analysis, we forget that everything relies on the flux. Are there any other comments?
So when you compare with Minerva or Minibone, which data are exactly those, the CC 0 pion events or what?
Yes, so the CC-Q-like events.
Yeah, Q-like, what could means a lot. But
Yeah, it means a lot. So,
as Callum was saying before.
Yeah.
Yeah.
So for Minibone, I think they were the first one, right, to do this kind of analysis. So they just called it CCQ, right, or charge quasi-elastic, and then Minerva came afterwards, and they did, yeah.
Yeah, no, because
it's not easy, yes, to disentangle. I mean, to differentiate between this one and the other contribution, right?
Because can you do the calculation for argon or no?
This will imply these nuclear models, right? Like,
yeah,
because you would have to include final state, for instance, interaction, right, inside the nucleus is not very easy, right?
Yeah, I know, because, for example, we have some data from Argonaut. They have large errors, but it would be nice. Neutrino and neutrino data, by the way. So here, just comparing neutrino data, right?
neutrino here we did.
What
Yeah.
about anti-neutrino
We
data?
could do it, right?
So I
It's
don't
no
know. I was
problem,
just
it's
looking at the plot that I can show
Anti-neutrino-
you, but that's argon, of course.
It's not a problem, yeah. So the goal will be to basically take the input from lattice QCD and put it already in the generators, yes? To say this part is what we think is well known, yes? And then we have to work on the other parts.
Which is a big part. Sorry?
In some way, liquid argon data would be better, even maybe ideal for some of this, because let's say you're trying to subtract events where your pion, undergoes an FSI. There's probably something happening in your event. There's at least like a shower of low energy stuff that comes out of the nucleus, which you might miss, but in mini boon, Calum has his hand up, so he's next. And alternatively, if you look at your hadronic system and you look at events where you have multiple nucleons coming out, that would also be very insightful for this whole debate. Because basically, if we do think that 30% of the cross-section comes from these events, then you should see multiple nucleons and great multiplicity. And if you look very carefully at the composition of things which look very quasi-elastic in your detector versus they have multiple hadrons versus they have pions, because some of these events can also be in the dip region, they could actually be pion production events. So I think looking at the hadronic system could be a lot in the complementary way to what was discussed here. I mean, here we're just talking about the lepton side, but maybe this could even be decisive to solve this thing long term. Well, anyway, you have your hand up, so.
So I wanted to pick up on what you just said about being able to see something coming out of the nucleus. So actually, this is a problem for Minerva, because if you try and define a very clean signal to measure a cross-section of, it's very hard when you see too much, in a sense, because so like CC0 pi for Minerva, they have cuts on the recoil energy. But the problem is that is very difficult to map to any like underlying true variables. But it's sort of the only handle they have, right? And so they cut away some portion of what we would call 2B2H, right? If it exists with the strength that is at, right? Let's drop that for a second. But they cut away something that might be relevant. Whereas mini boon in their uncorrected measurement don't do that because they can't see it, right? So it's actually a very clean measurement. They see, they say we see a muon and we don't see any pions above a certain threshold. And so I would just add that note of caution to the different, when you consider which type of data might be more useful than others. There are sometimes very hidden caveats that make it challenging.
Yeah. But I'm just saying that for liquid argon, this could be an opportunity.
We could try it.
With Argonaut, we started doing that. And we have some data, of course, with the statistics that we have, but now Microboon is also. Yeah, exactly. Microboon is doing that now. So, okay.
We could compare, right? It doesn't hurt.
Yeah, I can give you the
It would be
Argonaut data
correct,
if you
yeah.
want with the error, with
Yeah,
the large error, because the statistics was very
Would
low.
be
But
interesting, yeah.
yeah,
very
okay.
interesting.
And then Microboon can do certainly much better.
Yeah, T2K, I was wondering, yeah.
I think we should wrap it up for now. So is there any last urgent comment?